Okay, so following up on the previous video, we're going to find the electric field at point A in space due to a charge Q from a certain distance. And for simplicity's sake, let's simplify this example and just consider when the charge is positive and what the corresponding electric field is. So now I'm going to just blow this picture up a bit. Okay, so by now you must be familiar with the idea that a vector can be broken down into its components, its x and its y direction, as so. Here are the x and y direction of that electric field. So how do I describe this mathematically? In the most simplest way, E with a bar over the top, which is how I will designate it as a vector. In other text, you will see it in bold. So here, I see that there will be an EX I hat plus an EY J hat plus an EZ K hat. So this is how I can describe that vector in three-dimensional space, where I, J, and K correspond to the parts of that electric field that point in the x, y, and z direction, respectively. And the corresponding components are EX, EY, and EZ. For simplicity's sake, we're just going to consider this two-dimensional vector in our picture. So we're going to neglect the z or the k hat component. Now, you might also see this written alternatively in this form. And here, r hat is just a unit vector. This unit vector will indicate what the direction of the electric field is in the x, y, and z component, respectively. We'll talk more about that in detail in another video. So, for now, I just want to discuss what is this r squared here. So this r is the distance from the charge to the point in space whose electric field we wish to know. So here, this is what r is. Now if I know what the point A is, meaning its coordinate positions, which are xa, ya, I can easily determine what that distance r is. So along the x-axis, I have xa. Along the y-axis, I have ya. And lo and behold, you get a right triangle. So you can use Pythagoras' theorem to describe that distance r as the square root of xa squared plus ya squared, using the Pythagorean theorem. Okay, but what about describing ey and ex? Okay, so now here's where we're going to translate this ey vector over here. And now we're going to take this triangle out of context. So now you see over here that the hypotenuse here is our electric field vector E, and it is its magnitude. Notice there's no bar on top. In other notations, people write the magnitude with the bar on top along with the absolute values, but that's just notation. So now you see over here the x and y components can be written in terms of an angle. But what is that angle? Well, let's say we go back to our original picture and define this angle theta. We see that along this line over here, that the angle theta is also over here. And this is just by geometry, corresponding angles. So now, I see in my picture out here, this is where theta shows up. So now let's take a look at this. How can I express the x and y components of the electric field in terms of that angle? Well, if I go back to my original expression here for a vector, I see that Ex is adjacent to the angle, so that is the same as E times cosine of theta. Likewise, Ey is E sine of theta. So what about E itself? Well, like I said before, this E is the magnitude of that vector. So we see E is K times Q over R squared. And we already saw for R prior, so we see that as K times Q over the square root of XA squared plus YA squared. So, all in all, when I plug this into here, I can simplify how I express this entire electric field vector. E is equal to E cosine of theta I hat plus E sine theta j hat, and I can factor out this E because it is in common in both of these vector components, and I can say my electric field vector is equal to E times cosine theta I hat plus sine theta j hat in brackets. And then, to simplify it all, I plug in the magnitude of my electric field, which is K times Q over the square root of XA squared plus YA squared multiplied by cosine theta I hat plus sine theta j hat. And that is our electric field as a vector in terms of its x and y components.